Space appears empty, a vast darkness stretching beyond imagination. No air, no ground, no up or down. And yet, planets orbit stars, moons circle planets, galaxies rotate in immense spirals. Something invisible is shaping everything. We call it gravity. But how can gravity exist in outer space if space is almost completely empty? The illusion of weightlessness. When we see astronauts floating aboard the International Space Station, it seems obvious. There must be no gravity up there. But that assumption is wrong. At the altitude of the ISS, roughly 400 kilometers above Earth, gravity is still about 90% as strong as it is on the surface. Astronauts are not beyond gravity, they are inside it. So why do they float? Because they are falling. The International Space Station is constantly falling toward Earth, but it is also moving sideways fast enough, over 28,000 kilometers per hour, that it keeps missing the ground. This continuous free fall is what we call orbit. Inside that falling laboratory, everything falls together. Astronauts feel weightless, not because gravity is gone, but because nothing is pushing back against their fall. On Earth, the ground stops us. In orbit, nothing does. Newton's universe. Isaac Newton was the first to describe gravity mathematically in the 17th century. He proposed a radical idea. Every object in the universe attracts every other object. The force depends on two things: mass and distance. The greater the mass, the stronger the attraction. The greater the distance, the weaker it becomes. This simple relationship explained the motion of the moon, the fall of apples, and the paths of planets. Most importantly, Newton showed that gravity does not require air, contact, or a medium. It acts across empty space. But Newton himself admitted something unsettling. He could describe how gravity behaves. He could not explain what it is. How can two objects influence each other across a vacuum? For more than 200 years, no one knew. A new picture of reality. Albert Einstein changed the story in 1915. His theory of general relativity redefined gravity entirely. Gravity, he proposed, is not a force, it is geometry. Space and time are not separate. They form a single fabric, spacetime. Mass and energy bend that fabric, and objects move along its curves. Imagine placing a heavy sphere on a stretched sheet. The sheet bends. A smaller object nearby rolls toward the curve, not because something pulls it, but because the surface itself is warped. In the real universe, the sun bends spacetime. Earth moves along that curved path. What we perceive as gravitational attraction is actually motion through curved spacetime. Gravity exists in outer space because spacetime exists everywhere, even in regions that appear empty. Space is not nothing. When we say space is empty, we mean it contains very little matter. But empty does not mean non-existent. Spacetime itself is real. It can stretch, it can bend, it can ripple. We observe this directly through gravitational lensing, where massive galaxy clusters bend light from more distant galaxies. Light follows curved spacetime. The bending of light is measurable evidence that spacetime is not flat. Even far from stars, spacetime remains. And as long as spacetime exists, gravity can exist. It may become incredibly weak across vast distances, but it never truly disappears. How far does gravity reach? Gravity has no boundary. Its strength decreases with distance, following what scientists call the inverse square law, but its influence extends infinitely. Earth's gravity reaches the moon. The sun's gravity governs the entire solar system. On even larger scales, gravity shapes galaxies and galaxy clusters. Without gravity, stars would not form, planets would not orbit, Galaxies would not hold together. Structure in the universe exists because gravity sculpts it. Invisible mass. Dark matter adds another layer to the mystery. When astronomers measure how galaxies rotate, the visible matter is not enough to explain their motion. Something unseen provides additional gravitational influence. We cannot detect dark matter directly through light, but we detect its gravity. Its presence reminds us that gravity does not depend on visibility. It depends only on mass and energy. What gravity reveals is often more important than what we can see. Gravity can move. In 2015, scientists observed gravitational waves for the first time, ripples in spacetime caused by merging black holes. These waves were predicted a century earlier by Einstein. Their detection confirmed something profound. Spacetime is dynamic. Gravity is not static. It can vibrate. It can carry energy. Even in the deepest vacuum, spacetime is alive with structure. Gravity exists in outer space not because space is filled with some invisible substance pulling things together. It exists because space itself is part of the structure of reality. Mass bends spacetime. Objects move along that curvature, and what we experience as gravity is simply the natural motion through that geometry. Astronauts float because they are falling, planets orbit because space-time is curved, galaxies spin because invisible mass shapes the cosmic landscape. Outer space is not empty nothingness. It is a vast, structured fabric, and gravity is the signature of its shape. The deeper we look into the universe, the less empty it becomes.